Hello and welcome to Live from NOIRLab at Kitt Peak. This is Rob Sparks and I'm your host with our moderator today, Jamika Marshall. Our guest is Sarah Logsdon of NOIRLab in Tucson. Sarah's going to be telling us about an exciting new instrument on Kitt Peak called NEID, which is going to give us an unprecedented look at exoplanets and unprecedented information on them. And I'm really excited to be hearing about it from her perspective. Remember, if you have any questions or comments, you can enter them in the chat box and Jamika will relay them to our guest, Sarah. First, I'd like to tell you a little about Kitt Peak. Kitt Peak is funded by the National Science Foundation. It is a NOIRLab facility. It was founded in 1958, is located about 55 miles southwest of Tucson on land leased from the Tohono O'odham Nation. We are indebted to the O'odham people for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to over 24 telescopes and 2 radio telescopes. Now, I'd also like to share with you before we begin, and this actually connects in with our guest, one of our recent images of the week. If you go to the noirlab.edu website, you can find our images of the week. And this is actually a picture of the WIN telescope, which is where NEID is located. It was taken in October of 2018. I was the photographer for this one. I was on Kitt Peak and there were glowworms out. So I decided to put my camera on the ground and take a picture of a glowworm crossing the street in front of the WIN telescope. This just shows you some of the diverse wildlife at Kitt Peak. I'd worked there for many years and had never seen the glowworms until finally one night the climate conditions were right and they were out and it was a magical evening and I was happy to see it. So if you're ever at Kitt Peak at night, I hope you get up there at some time and maybe, if you're really lucky, the glowworms will come out to greet you. So now let's meet our guest. Dr. Sarah Logsdon is an assistant scientist at NSF's NOIRLab. She also serves as the NOIRLab instrument scientist for NEID, a precision radial velocity spectrometer recently installed at the WIN 3.5 meter telescope at Kitt Peak. Before coming to NOIRLab, Sarah was a NASA postdoctoral program fellow at NASA's Goddard Space Flight Center, where she worked on the development of the NEID port adapter system, which is responsible for sending starlight from the telescope to the NEID spectrometer. She received her PhD in astrophysics from the University of California, Los Angeles. So please, let's bring on Sarah Logsdon here and meet her, and I will stop sharing so Sarah can share her screen and presentation. Welcome, Sarah.
Thank you very much, Rob. I really appreciate that nice introduction, both to NEID and WIN and to myself. Let me see if I can share my screen here.
Okay, take it away.
Can you see the slides okay, Rob?
Yes, looks good.
Awesome. Well, hello, everyone. Thank you so much for coming today. It's really my pleasure to be telling you a little bit more about exoplanets and measuring and characterizing these exoplanets with the NEID instrument. I've split this talk into 2 main sections. The first is really grounding us in what is an exoplanet, what do we know about exoplanets right now, and how do we actually find these exoplanets? Then I'll transition more into talking about NEID and how NEID is powerful for characterizing exoplanets and finding exoplanets, and some of the challenges that we face trying to measure Earth-like planets around sun-like stars. And I will end the talk showing you an image from the first light with NEID, which is really exciting to me. And it's an image of this star, the N planet that you're seeing right here. This is an artist rendition of 51 Peg. This is one of the very earliest exoplanet discoveries in 1995. And the folks who discovered 51 Peg B, the planet, actually won the Nobel Prize last year for that discovery. So just to make sure we're all on the same page, I wanted to actually define what exoplanet means for all of you. Astronomy has a lot of buzzwords. So if you catch me using a buzzword that you don't understand, please put it in the chat and Jamika will let me know and I'm happy to explain it to you. But an exoplanet, or they're sometimes known as extrasolar planets, is just a planet that orbits a star other than our sun. So Earth orbits the sun, so it's a planet. But if we found an Earth-like planet around another star, we would call that an exoplanet. And to cut straight to the chase, for those of you that really like numbers, over the past decade or so, we have really found a treasure trove of planets outside of our solar system. And a lot of that is due to 2 NASA missions that have launched in the last decade, and I will talk a little bit more about those later. But if you really like the numbers, I highly recommend going to exoplanets.nasa.gov. They have this really awesome dashboard where they have nice view graphs of the number of confirmed planets, the types of planets, new planets that are being found all the time. It's a really interesting resource. And so I'm just showing a little screen grab from a couple days ago. So as of a couple days ago, there were 4,292 confirmed planets, exoplanets, and even more exoplanet candidates that we still need to follow up on. And this nicely shows the demographics of those exoplanets. And you can see that actually most of the exoplanets that we have found are not Earths. They're bigger than that. They're Neptune-like planets and gas giants like Jupiter and Saturn. And these interesting planets called super Earths, we don't really have an analog for this in our solar system, but these are exoplanets that fall in the gap between Earth in our solar system and Neptune and Uranus. And you can see the terrestrial planets, these rocky planets like Earth, we've only found 163 that we have confirmed to date. So we still have a lot more work to do to really build a census of all of the types of exoplanets that are out there. And one of the big questions that we're hoping to answer by these studies is, can we find solar systems like ours? Are we unique, or are there tons of solar systems and tons of Earths out there? And I wanted to show this example because I find the system to be really interesting. This is Kepler-90, and right now it has the distinction of being the only other known system that has the same number of known planets as our solar system. So here in the figure, I'm showing you artist renditions of what we think that the Kepler-90 planets might look like compared to our solar system. Kepler-90 is not only interesting because it has the same number of known planets as our solar system, but its star is actually quite similar to the sun. So at first you think, oh, maybe we have found a solar system analog. But if we take a little bit of a closer look, we can start to see some big differences between Kepler-90 and our solar system. The first one you might see right off the bat, and that's the orientation of the planets away from the star. You can see that the general trend is similar. We've got smaller planets in closer to the star, and we've got bigger planets further away. But you'll notice that the biggest planet in this system is actually the furthest planet away from the star, whereas in our solar system, Jupiter is sort of in the middle. And this has interesting implications for how planets are formed and the dynamical interactions that they undergo. The other interesting thing that we'll show you right away that Kepler-90 is quite different from our solar system is if you actually compare the orbits of all the planets and how far away they are from their star. So what you're seeing in this figure on the right-hand side are the orbits of our inner solar system planets. So that's Mercury, Venus, and Earth, and how far away they are from the sun, compared to Kepler-90 on the left. And you can see that all 8 of the Kepler-90 planets orbit the star within the orbit of Earth. So that means that all of the planets are closer to their host star, Kepler-90, than Earth. So this is a very tightly packed system. And this has lots of implications for what the planets look like. For example, Kepler-90I, which is the red orbit that you see there, and in the blowout on the left, this is actually a super Earth. It's about 1.3 times the radius of the Earth. It's probably the closest Earth analog in the Kepler-90 system, but it's actually way closer to the star than Earth is. It's actually well within inside the orbit of Mercury, the closest planet to our star. And that means a couple things. It means that a year on Kepler-90I looks quite different than a year on Earth. It's only about 14 and a half days for the planet to go all the way around the star. It also means that Kepler-90I is really hot. It's about 800 degrees Fahrenheit. So you definitely wouldn't want to be taking a vacation to Kepler-90I. And this is just one example of the types of systems that we're finding. But there's lots of really cool and interesting exoplanets out there. And one of my favorite ways to think about them is actually using these fun space tourism posters that NASA has developed over the last few years. And I know other astronomers like them because when I visit their offices, they're full of these posters, and I wanted to show you because you can actually go to the website that's linked down there and print them out for yourself too, but also because they show the diversity of exoplanets that we are finding. So we have planets like Kepler-16b on the left that is probably known by the Star Wars fans as the Tatooine planet because it actually orbits 2 stars. And then we have planets that have very different gravity than we have on Earth. So you could be floating up in the sky or be really heavy on a planet that has a lot of gravity. We also are finding more and more planets around stars that are low mass. So they're both smaller and cooler than our sun. And that means that they're redder. And so there's a fun poster for Kepler 186f where the artist thought, well, perhaps because the planet is or the star is redder, that photosynthesis might work a little bit differently, and the shrubbery in Kepler 186f might be red. So there's tons of interesting systems out there that are really great to study. But how do we actually find these planets? There are many, many ways to find planets outside of our solar system. I'm going to talk about 2 of them today. And these 2 are the most popular and have found the most planets to date. And the one that has found the most planets by leaps and bounds is this transit photometry method, which you can also think of as the stellar dimming method. So what we do here is we take a telescope and we point it at a star and we just take images of it, pictures with cameras, and we continue to take images over time and measure how bright the star is. So here you're seeing on the plot, just a plot of that, the brightness on the y-axis as a function of time on the x-axis. And now if a planet passes in front of that star, it's actually blocking a teeny bit of the light, and we can make that measurement. So you can see that when the planet is not in front of the star, we have a level brightness, and then the planet starts to pass in front of the star, and you see a dip in what we call the light curve. And if that dip is repeatable, we call that a potential planet candidate, and we continue to follow it up. So this is the transit photometry method. The second most popular method is actually the method that NEID uses. This is called Doppler spectroscopy, or the radial velocity method, or maybe more colloquially, it's the stellar wobble method. And so this really capitalizes on the fact that we usually think of a star as a fixed thing with a planet orbiting around it. This isn't actually true because the planet has some gravitational pull that impacts the star. It moves the star just a little bit in a little tiny orbit, and it just makes the star wobble. And when it wobbles, that means that for part of the time in its orbit, it's moving closer to us, and part of the time it's moving further away. And as it's moving closer, the wavelengths of light get shorter, and we call that blue shifted. And as it's moving further away, the wavelengths of light get longer, and we call that being red shifted. And this is just like when you hear a fire engine going past you. This is what happens with the sound. As a fire truck is coming up behind you and getting closer, the sound waves are getting shorter, and the pitch of the fire engine's siren goes up. And as it moves in front of you and away from you, the sound waves are getting longer, and you can hear it drop in pitch as it moves further away. It's the same exact thing here. So I actually have 2 videos that illustrate this. Hopefully I can get them to run. So here we're seeing the big star in yellow and the dimmer, smaller planet. You can see that they're both orbiting. And this is if we were looking at it face on, but we're normally looking at it like this, edge on from our telescope. And you can see as the star is moving towards us, the light in the bottom is getting bluer. And as the star starts to move away from us, it starts getting redder. That's the same thing. That's the Doppler shift that we're measuring. And I have a similar video. It's the same exact concept, but I really like how they're showing the shift on the bottom of this video, because this is a lot more similar to what we're measuring with NEID. This is actually taking a spectrum. So a spectrum just means you're separating light into its colors. So you can see the rainbow down there, and you can see the rainbow is broken up by these black lines. These lines are actually absorption features. A star has chemical elements in it, like hydrogen and helium and sodium and calcium. And those lines have distinct discrete wavelengths. And if that line is absorbed in the star, that's actually blocking some of the light from reaching us. So this is the same concept. And you notice as a star is coming towards us, the lines are moving to the left towards the blue, it's being blue shifted. And as the star is moving away from us, the lines are moving to the right, being red shifted. And this is exactly what we're measuring with NEID, the moving of these lines from blue shifted to red shifted as the planet orbits the star. So great, we have two methods for finding planets, transit photometry and Doppler spectroscopy. Do we need two methods? Actually, yes, these methods are really complementary to each other and really useful because they tell us different things about the system. The transit photometry method tells us information about the planet's size in relation to the host star. So if you have a bigger planet, it's going to block more light from the star. It also tells us what the planet's orbital period is. That's how long it takes for the planet to go around the star once. We can actually just wait until we measure one dip and then two dips in the light curve there, and that'll tell us how long it took for the planet to go all the way around once. But Doppler spectroscopy tells us something different. It actually tells us about the planet's mass, which is also important. And the basic idea here is that if you have a more massive planet, it'll have a bigger pull on the star. And so you'll see the blue shift and the red shift will be stronger signals. And together, this is really, really valuable because if you have a size and you have a mass, you can calculate a density. And the density tells us something about what the planet is made of. So here I'm showing you a plot of planet size on the y-axis. This is what we get from the transit photometry method. And then planet mass on the x-axis. This is what we get for the Doppler spectroscopy method. And what you're seeing on this plot are a bunch of colored lines. And these lines represent different chemical compositions. So we have the bluish purplish line at 100% water at the top here. And then down here in orange, we have 100% iron, so something really dense and rocky. And then plotted on top of all of these lines are planets that we actually have both a transit measurement and a Doppler spectroscopy measurement for. And you can see, to no surprise, they're falling in different places, that some planets are more rocky and some planets are more watery or even more gaseous. And you can see actually in the lower left corner of this plot, we have both Earth and Venus. And it perhaps comes as no surprise that they're somewhere between the iron and the water. We are on a planet that is rocky, that also has liquid water. So its density is somewhere in between the two. And I want to talk to you a lot about NEID and the Doppler spectroscopy method. But before I do that, I want to give you a little bit of an idea of where we actually get these transit measurements from. So there have been two NASA missions that have been really critical in this. The first is Kepler and K2. It had a second mission that was known as K2, and then TESS, the Transiting Exoplanet Survey Satellite. So Kepler was the first one. It was launched in 2009, and it was active from 2009 to 2018, when a combination of a mechanical failure and running out of fuel meant that NASA had to shut it down. But Kepler has just been tremendous for the field of exoplanets. To date, there have been 2,412 confirmed planets that were discovered with Kepler. And if you remember from the first slide, we said there were just over 4,200 planets discovered to date. So a huge portion of those have come from Kepler. And then we have TESS, which was launched in 2018. So it's pretty new, and it's been running from 2018 to now, and it's been funded to continue running, which is fantastic. And it takes a little while to get confirmed planets. There are lots and lots of planet candidates coming out of TESS, but even so, there's still 66 confirmed new planets from TESS in the last 2 years, which is just fantastic. And there's a lot more to come from TESS. And you may ask, why do we need TESS if we already had Kepler? And that's a great question. And the answer is really that Kepler and TESS were looking at totally different parts of the sky. So the Kepler search method was to stare at one portion of the sky for as long as possible. So it got all the way out to 3,000 light years, but it only covered 0.25% of the sky. And TESS's strategy is a little bit different. TESS is actually covering the whole sky, but it only looks at each portion of the sky for a month at a time before moving to a next portion of the sky. And so that means that both Kepler and TESS are probing different planetary orbits. TESS can only see short period planets, whereas Kepler could look at much longer period planets. They're looking at different types of stars. Stars that are closer in to Earth, we can look for fainter stars, whereas Kepler at 3,000 light years, we needed to look at brighter stars. And as you can see, they were looking at different parts of space. So they're really complementary to each other and looking for different types of systems. So here's that density plot again, and I'm just showing that TESS and Kepler are really giving us the transits. But to do Doppler spectroscopy, we need precision instruments like NEID. So NEID, we finally get to NEID. NEID is an extreme precision Doppler spectrometer, and that is a lot of buzzwords. So I wanted to break them down for you a little bit. A lot of astronomy names are either named after someone or an acronym, but NEID is actually a word. It means to see in the language of the Tohono O'odham people. And as Rob told us at the very beginning of the talk, WIN and NEID are on the Tohono O'odham land, and we're really grateful that they give us the opportunity to make these fantastic discoveries from their land. So this is really to honor them. Extreme precision, NEID is really geared to pushing the limits of what is detectable with this type of instrument. And we'll talk a lot more about that as we go later into the talk. The Doppler effect, we've already heard a lot about. That's that changing redshift and blue shift as light moves towards us and away from us from the star. And then spectrometer. A spectrometer at the most basic level is just the instrument that breaks light up into its colors like a prism. Colors are equivalent to wavelengths. And before I get into the details of NEID, I really have to give a shout out to the NEID team. This is a massive team effort. This is certainly not just me. NEID is a high precision instrument, and we have people working all over the country and in other parts of the world on NEID. The spectrograph itself was built at Penn State. So the picture here is actually just one small subset of the team at Penn State for the pre-ship review when we got ready to send it out to WIN. NEID really came out of a joint effort by NASA and the National Science Foundation to invest in exoplanet research through a program called NN Explore. And it was really responding to a need to have the ability to follow up missions like Kepler and TESS that are giving that transit information to give astronomers a publicly available resource for getting the Doppler spectroscopy, which also is a help for the next generation of NASA space station missions like JWST, the James Webb Space Telescope, where we hope to actually be starting to measure the atmospheres of some of these planets. And I see that Jamika might have a question for me, so I'm going to pause and take that.
Yes, thank you so much, Sarah. Fantastic talk, which has been reflected in the comments, of course, too. And we do have a question for you.
Sure.
So this is in reference to the Doppler effect you were talking about earlier. And we have a comment from Alan Jackson. Alan says, open source software is available for stellar transit monitoring from TESS data, TESS Latte and Eleanor, just to name a few he puts here, and asks, is there equivalent software for Doppler spectroscopy detection method?
That's an excellent question. Thank you very much, Alan. The answer is partially yes and partially no. So as we will see as I continue through this talk, these instruments are quite complex. And so they usually have their own unique pipeline for reducing all of the data. But there is a big move to have open source radio velocity analysis code. So there's on GitHub, I don't know if you're familiar with GitHub, but a lot of the data for actually doing the analysis after you've cleaned up the data for things like noise sources and done your calibration work, which we'll talk about in a little bit. Then you want to actually take and measure your radial velocity. There's some open source code to do that. I hope that answers your question. So I'm going to talk a little bit more about the nitty-gritties of NEID in a second, but I just wanted to give you a big picture of how NEID works. And so obviously you want to start with a target star that you want to look at. So you need to find the target star. That's what I'm showing on the left. And then we actually use the wind telescope to collect the light. And once we have the light, there's actually a third mirror. So how the wind telescope works is we have a big primary mirror that's 3.5 meters across. That's about 11.5 feet. And that's the big light collecting bucket. And then that light is reflected up to the secondary mirror, which you can see in black right here. And then that light is sent down to a third mirror, which lives in here. This is not unique to have a tertiary mirror on the telescope, but it's very important for WIN because NEID isn't the only instrument that operates at WIN. And there are instruments on the various sides of the telescope, the various ports. And so this mirror can actually turn to the various ports. So you don't have to uninstall and reinstall an instrument to observe with it. You just turn the mirror around and then it's facing that instrument. And so NEID has its own port. That's what you see in the picture on the right. These black boxes are the NEID port adapter, and we'll talk a little bit more about that too. But the port adapter collects the light from the telescope and sends it to the NEID science fiber, which sounds easy, but is actually quite complicated, as you'll learn in a few slides. And then that light has to get sent to NEID. NEID doesn't actually live on the telescope. It's not attached to the telescope. So we use fibers to send the light from the port adapter down to the spectrograph, which is the gray thing you can see right here in the image on the lower right. So that's how we get light from the star down to NEID. And then we have a CCD, a detector, just very similar to the detector in your phone, just a whole lot bigger with a whole lot less noise that actually captures the data for us. A couple slides ago, I said that NEID was an extreme precision Doppler spectrometer. And you might be wondering what that means and why we need it. Extreme precision is really driven by the science. One of the key goals in exoplanet studies is to find planets like Earth, to answer the question, are we alone? Is Earth unique? And so we want to find Earth-like planets around other stars that are in what we call the habitable zone, which means that they would be amenable to having liquid water on their surface, somewhere that organisms like humans can live. But that's hard to do. An Earth-like planet around a sun-like star has a radial velocity, so the shifting of those lines, of about 10 centimeters per second. That's 0.22 miles an hour, which I'm pretty sure is about the speed of a slug. So imagine trying to make that measurement to measure the speed of a slug of a star, a planet orbiting a star out in space. It's a tricky thing to do. And to put that in some physical perspective, here I'm just showing a lattice of silicon atoms. Most of optical detectors are made of silicon. And a 10 centimeter per second shift is a shift of about 6 or 7 silicon atoms. And on the NEID detector, that's about 1/6000th of 1 pixel. This is a very, very, very precise measurement. And there's a lot of things that make this challenging, and I'm going to talk through a few of them now. The first is the instrumental precision and the instrumental stability, and the second is stellar activity. And I'll talk more about that in a bit, but I want to talk a little bit about the instrument stability. That's stability like pressure and temperature stability, calibration accuracy, making sure throughput is making sure we have enough light getting to the detector. All of these things matter. And NEID is expected to reach an instrumental precision of less than about 30 centimeters per second, which isn't quite 10 centimeters per second, but is really pushing the envelope to get there and as a path to get there. And that starts outside of NEID, that starts with the facilities at WIN. So here I'm showing you just a cutout of the wind dome. So it actually has 3 floors. On the top floor is where the telescope lives. And then we have a second floor, and then we have a ground floor. And NEID actually lives on the ground floor, which I like to sometimes call the basement. But we don't put NEID in the basement in the way that you would think of putting some old boxes in your basement. We don't want NEID to get dusty. We don't want NEID to get cold. We've actually built a special room just for NEID, and that's what you see here in blue. Completely new room. It did not exist at the WIN before. The walls were not there for putting NEID in. And this is what the room looks like before we put NEID in. And you can see it's very nice and clean. This is a clean room environment, just like you would see in a lab. And NEID goes in the right-hand corner over here. And why do we need that? We need it for thermal stability more than anything else. So not only do we need the room to be thermally stable, we also need the instrument itself to be isolated as much as possible from thermal changes and vibrational changes. And a lot of work was put into this design. This is a design that's actually the next generation of a design that was made for the HPF instrument, which is a similar instrument to NEID, but covers different wavelengths, and it's installed in the Hobby-Eberly telescope, which is in Texas. And then NEID is over here on the right. So NEID starts at this lower level. This is actually a reservoir for liquid nitrogen, which we use to cool NEID's detector and make sure that we keep the noise down. And then up here at the second level, this is where all of the NEID's optics are. And you can see these little orange squares along the side and also on this lid right here. And those are all heaters. So we actually use the liquid nitrogen to cool, and then we use the heaters to keep all of the optics at a very, very stable temperature. And when I say very, very stable, I mean better than a millikelvin, which is about 2,000th of a degree Fahrenheit. At Penn State in the lab, when they were building NEID, they were able to achieve less than a millikelvin over a 30-day period. The temperature didn't change any more than that. And WIN is actually has a more stable room to begin with than the NEID room. So we expect hopefully even better performance over the long term with NEID at WIN. So besides keeping the instrument itself stable, there's lots of things that we do to build up around it to make sure it stays that way. So here I'm showing you 2 pictures of NEID. On the left is a rare site. If you went to WIN today, you wouldn't see that. This is actually the spectrograph itself. While we were installing it, we were putting the lid back on actually. And then on the right, you can see, I can't see that instrument anymore. I just see these gray walls. That's actually NEID's thermal enclosure. And what that does is it makes sure that if the room were to suddenly warm up, which it shouldn't because it is also well controlled, that wouldn't immediately shock NEID. It would be a more gradual change. And this is actually an industrial thermal enclosure. This is very similar to a meat locker that you would see in the food industry. In addition to NEID and its room's stability, we have to make sure that the light that gets to NEID that comes from its port adapter is really stable. So again, these black boxes are all part of the NEID port adapter. This is the main bench here over here on the left with the NEID sticker on it. And then we have a smaller subsystem here, and then a big electronics box to make sure everything's powered. And these set of boxes do a lot of things. First, they acquire the target star, and then they stabilize the star's position on a fiber, which you'll see in a few slides. They also are responsible for correcting for atmospheric dispersion. So our atmosphere actually acts kind of like a prism. And the further you go to horizon, the more atmosphere you look through, and it can actually split your light a little bit into that rainbow like a spectrograph. We don't want that because that means that we might not be putting all of the light from the target star down the NEID fiber, and it will change as we change elevation. So we actually have prisms inside the port adapter that correct for that. They're equal and opposite to what the atmosphere is doing. We also need to make sure that the telescope stays nicely focused. We don't want any fuzzy images, again, sending light off the fiber. We can also send calibration light through this bench. So this is a very, very important subsystem for NEID. And I won't quiz you on this at all, but this is a light path diagram just showing you all of the things that are happening inside that bench. So here are those two prisms that I was talking about that correct for the atmospheric dispersion. Here's a camera that we use on the left over here for guiding to make sure that we're keeping the target star where we think it's going. We can send calibration light up through here in the bottom, but the biggest, most important things are these two fiber heads right here where we send the light to NEID. And one of those heads looks like this. You can see there's 4 little circles and 3 big circles. The little circle in the middle is actually the science fiber, and it is about the diameter of a human hair. It's about 62 microns. And that's where we need to put and hold very stably our target star. So you can see what a challenge that is. The other 3 small ones are spare fibers and a sky fiber, so that we can measure what the sky background is doing and correct for that as well. And then the 3 bigger circles are actually coherent fiber bundles that we can send the star to make sure we know exactly where we're pointed. Another important aspect of NEID is calibration and the data reduction, which was what Alan's question was getting at. And we have a really stable way for calibrating NEID data that's using this thing called a laser frequency comb. I think of it as a wavelength ruler. As you can see from this cartoon image, it emits light at very discrete, very well-known wavelengths. So it really helps us wavelength calibrate NEID. And then this other important thing that I haven't got a chance to talk about yet that really impacts our ability to get to those 10 centimeters a second is stellar activity. So I often think of the sun as this cartoon picture that we always see, this yellow happy thing. But in reality, the sun looks more like the picture on the right. You can see it's not so smooth. There are bright spots and dark spots, and there are flares. And all of this is added noise into our data. So we need to have ways to understand and correct this. And this is still a very active area of astronomical research. So NEID actually addresses this in 2 ways. So NEID is making a spectrum. If you remember the rainbow that we saw earlier in the talk with the dark lines, I was saying that those are things like hydrogen and sodium and calcium. All of those lines are useful because they tell us how much stellar activity there is in the star, and we can monitor how they change to tell us how much stellar activity a given star has. So that's just what you're seeing here on the plot, is measurement precision as a function of stellar type and temperature as a function of wavelength. And all of the lines that are called out here are lines that we can use to monitor for stellar activity. We also have a new and exciting addition to NEID, which is actually a solar telescope that we can use during the day. So we can image other stars at night, and during the day we can measure the sun. And the sun is nice and bright, so we don't need a 3.5 meter telescope to look at it. We actually use this tiny little telescope that you can see on the left that's sitting on the roof of the wind telescope. And here's a close-up of it on the right. We actually have 2 things happening here. We have the solar telescope itself, which is the snout that's sticking out here in the back. And in the front, we have what is called a periheliometer, which is really just a cloud measurer. It measures how much sunlight it's getting over time. And if a cloud rolls in, the numbers drop right off. So this is really helpful for us when we're analyzing the data. We take the spectrum of the solar data from NEID and the periheliometer, and we say, oh, it was a terribly cloudy day today. We're not going to get useful data, or this was a perfectly clear day. This is a great way to monitor the sun. The sun is our closest star. It will tell us a lot about the other stars that we're looking at with NEID. So what is NEID's expected science gains? Here I'm showing you a plot of stellar temperature on the y-axis. So you can see we've got stars like our sun up here on top and really red small stars down here on the bottom. And as a function of orbital period, here is where all of a lot of different planets lie. And you can see that TESS in its normal survey only probes really short period planets, but there's a part of TESS that is always looking at the ecliptic poles. One of its cameras is always looking there, so it can probe much longer period objects. So all the objects to the left of this line are at the ecliptic pole, and the types of planets around the types of stars that tests can look at. And we've got a bunch of different lines here. This HARPS line that says 50 centimeters per second on the lower left, that's the state of the art of what we're doing now. And then the 3 NEID lines are our expected precision for NEID if we observed a star for 5 nights a year, or 30 nights a year, or 50 nights a year. And you can see the more measurements we can make, the more precise we are, and getting to smaller planets on longer orbital periods around fainter stars. So what is NEID up to today? Well, we're actually working to bring NEID back on sky right now. I was actually up at the telescope yesterday, starting to bring some of the NEID subsystems back online. So NEID was actually delivered to WIN last fall, and we began our commissioning effort, which is testing all of the NEID's components to make sure that they work like we expect they do. And we were in the midst of that when we were paused due to the COVID-19 epidemic, which actually shut down the observatory for about 7 months. But we just got cleared to go back to the telescope, and we're working really hard to get NEID restarted in a way that's slow and safe, so that we can keep it up and running for years to come. And I told you I wanted to end with a fun picture. So this is actually NEID's first light image. So this was the first time we got it on sky and pointed to a star that we knew had an exoplanet around it. And that was 51 PEG and 51 PEG B, like I talked about in my very first slide. So here on the left, you're seeing the wavelength coverage of NEID. NEID has a tremendous wavelength coverage. Basically the whole optical wavelength range from basically the near UV, where the calcium H and K stellar activity indicators lie, all the way almost up to the near infrared. And then we've got a zoom in on some of the lines. And what you're seeing here is actually 2 lines taken simultaneously. The first line that's solid with the little gaps, that's actually 51 PEG. And those are the absorption lines that I've been talking about. And then next to it is the light from our laser frequency comb, which is those very precise, very discrete wavelengths that we use for doing calibration with NEID. And this image was put together by Gumi Stephenson. He's a member of a NEID team and is a postdoc at Princeton University. So I thank him for putting this awesome image together. And that's the last talk, or the last slide in my talk. Hopefully not the last talk. There will be many, many more NOIRLab talks. But thank you so much for your attention. I've really enjoyed sharing NEID with you today.
Thank you, Sarah. That is fantastic. I mean, I was lucky enough to be up there when NEID was delivered last fall, and I met a lot of people from the team, and you're right, it is a fantastic team you have working up there with lots of great people on it. So, Jamika, do we have any comments or questions from the chat room?
I do have some questions. So first of all, again, from the chat, we're just getting lots of support and that this is a fabulous talk. So thank you so much. Exoplanets definitely is, I believe, on the radar for a lot of people who are at least interested in science or watching any sci-fi series. Exoplanets is a common household term now, whereas 20 years ago, it was unheard of. So could you tell us a little bit about how exoplanets are named? You were telling us about 51 PEG, right, has an exoplanet, and you call the planet 51 PEG B. How do they get these names?
Yeah, this is an excellent question. So usually exoplanets don't get their own individual names like we do in the solar system. Usually they share a name with their host star. So the host star is 51 PEG, and then the first planet that is found around 51 PEG gets a lowercase b designation. So if we were to find another star around 51 PEG, the 2 stars would be 51 PEG capital A and 51 PEG capital B. And if you find a planet around it, they become lowercase b, but they never get to be A because A is always the host star. So the more planets you find, you just keep counting up letters. So like Kepler 90, Kepler 90 has 8 planets. So that's A, B, C, D, E, F, G, HI. And it doesn't have anything to do with where they are in their orbits either, because we don't always know that when we're discovering them. It's really the discovery order.
Okay, that makes a lot of sense. And I'm really glad you pointed out that no planet can have the A designation.
Yeah.
Because it makes sense.
That confused me when I first was learning about planets. I'm like, can it be little a? But no.
Yeah, that can. I had that question when I first learned it too. So yeah, a lot of us had that. Can I ask a follow-up question about naming planets?
Sure.
We have 51 Peg B. We also have Kepler 90. So there's somehow that some are named after stars, but some are named after the mission. So there's a little bit more to the naming than that.
Yeah. So usually they're named after the mission. So stars that have planets that were found with Kepler may actually have another name entirely. They might have been named for another mission that found them originally. But then when Kepler finds them and finds a planet around them, they can have a second name, which is Kepler. And then the planet is named after the mission that found them.
Okay, thank you for clarifying that, because, and Rob, I appreciate that follow-up question, because it leads to the next one that I was going to ask as well too, just looking through a few of the comments here. As far as exoplanet detection methods go, of course, you went through the various kinds and which ones that NEID is using, but just in general, with all of these detection methods, is our regular everyday guests in the audience right now were to go outside and look up in the nighttime sky, out of all those stars that we see up there, Sarah, on average, how many planets are around each star?
Oh, that's a fantastic question. And I'm not up on the latest, but we think that most planets have, or most stars, I'm sorry, have planets around them, that it's much more common to have planets than not have planets.
And you did mention the Tatooine planet earlier. For those Star Wars fans, will definitely recognize that. So that's a planet orbiting 2 stars. So how common is our binary star system?
I don't think we actually have enough statistics to say that really robustly yet. It's a lot harder to detect a planet signal around a multiple star system, because we even have trouble when we're first discovering a star with a transit method. We have to decide whether or not there's actually a planet around it, or if there's another star, or something that's a little bit more massive than a planet, like these objects called brown dwarfs. So it's a tricky thing to do when you start getting into the multiple planet systems, because sometimes, and multiple star systems, because you don't see just one dip in that light curve, you see multiple dips. And if they're passing in front of the star at the same time, the dips might overlap with each other. So the more complicated the system is, the more follow-up we need to do to riddle out what's actually happening in the system.
Thank you so much, Sarah, for answering all of our questions so clearly. And I did put a link in the chat to the to the WIN telescope in general, but then to the press release, NASA's press release about NEID, and to a few of your current images that you have there. And just my last question here, for anyone who's interested in looking at the data from NEID, is that publicly available at some point in an archive that students can maybe use and work with and learn more about exoplanets?
That's a fantastic question. And the answer is yes, it will be eventually. It isn't yet. So how NEID works is astronomers propose to use NEID, and when they get time, they usually get what's called a proprietary period, which means that they have time to take the data and analyze it and publish it. But after that proprietary period is over, yes, the NEID data will go to an archive. We are actually paired up with NEXI, which is an offshoot of NASA, and they're actually going to host our archive for us. And they're actually responsible for doing the data reduction of NEID as well. So if an astronomer proposed to use NEID, we take the data at the telescope, and the telescope gets sent to NEXI, which is in California, and they reduce the data and they come up with a preliminary RV measurement and everything. And that goes to the users. And once their proprietary period is over, that data is available to the entire community and anyone who wants to look at it.
That is fabulous news for, I'm sure, a lot of people who are watching this now or will watch it later, to know that this fantastic data will be available.
Absolutely.
And we have 2 more questions from the YouTube audience. If we can, we have time for that, Rob? Yes, looks like we still have about 8 minutes. Okay, so this is from Ariel Vallejos. Thank you for joining us, Ariel. So the question is, 100% of the instruments, so it's a question, are 100% of the instruments manufactured in the US, or is there a collaboration with other countries?
So I'm going to answer this a little bit more broadly than just for WIN, but I'll answer for WIN and NEID as well. So NEID was built at Penn State University and the University of Wisconsin in Madison. They built the port adapter in Madison. But the NEID team covers the country and has team members in other parts of the world. One of our key collaborators is actually in Australia, and he designed the optics for NEID. That was an incredibly important part of NEID development. So we have collaborations from outside the country. And in general, especially as we move to these larger telescopes, we are building more and more international collaborations. It's becoming more and more important. So yes, there are pieces of instruments and full instruments that are built outside of the United States in astronomy.
Thank you. That's a very complete question, very complete answer, and I'm really glad that you gave the extra details because it really does help give us an insight into this whole process and how things come together. And your presentation, Sarah, has been so engaging that we have Alan Jackson asking, are your slides available? Will they be available someplace on a website that you control, or will he just have to enjoy rewatching this and watching the slides from our recorded version on NOIRLab YouTube channel?
So currently we're only planning to have these on NOIRLab and on the YouTube channel, though most of the figures in my slides I've taken from published resources, and I tried to put captions with credits for all of them where you can go find them. So hopefully that's a helpful resource for you.
Thank you so much, Sarah. And thank you everyone in our NOIRLab YouTube Live audience. We really appreciate you being here with us, and we have just a few more minutes left. So if you have one last question or comment for Sarah, please feel free to drop it in there, and I'll take a glance real quick in the last few minutes. Over to you, Rob.
Okay, well, thank you, Sarah. That was absolutely fantastic. Like I said, it amazes me how thermally stable that you have to keep that instrument to get those results of that precision. It's just absolutely incredible. And I've learned more things. Thank you for the talk, because I learned more things for myself when I give tours at WIN in the future. Hopefully, if I ever get to give tours of WIN again after the post-COVID world. But I also have one last interesting thing I'd like to just bring up, which this is funded primarily by NASA, is it not?
Yeah,
it is the funding of this?
It's a joint program between NASA and the National Science Foundation. So both of them have funded NEID.
Okay, cool. I thought it was, but I wasn't 100% sure how that all shook out in the end.
Yeah, so there's actually a program called Explore, which the two N's stand for NASA and the National Science Foundation, and NEID is just a piece of that, and they support other exoplanet efforts as well.
Okay. Well, do we have any last minute questions in the chat, Jamika?
No last minute questions, but a thank you and a really super cute emoji from Ariel Vallejos for your response.
Oh, thank you, Ariel. I hope you enjoyed the talk. Thank you for listening.
And Jamika, I believe next week is our Live from NOIRLab at Gemini, correct?
Yes, next week, Live from NOIRLab will be here in Hawaii, and our host will be Alyssa Leilani Losi. So stay tuned here to the NOIRLab channel, YouTube channel, right here next week, Wednesday. It's going to be 5 p.m. MST.
And 2 p.m. Hawaii Standard Time.
Exactly. Yes. Thank you so much, Rob. 2 p.m. HST with Alyssa Leilani Losi as the host, and I will be moderating again. So we look forward to having you in the audience.
And I just say, if you want to get all the notifications for when these events are coming up, you can follow us on Facebook, NOIRLab Astro, or NOIRLab Astro on Twitter. Also will be a way to get all the updates as well. And of course, NOIRLab Astro on YouTube. And there's even a NOIRLab Astro Instagram. So we have all the channels covered, and we managed to find NOIRLab Astro as the common name we could get for all of them. So thank you once again, Sarah. That was absolutely fantastic.
Thanks, everyone.
Okay, and signing off, we'll see you next